I would now like to call upon our next speaker, MatteuFullana.
Hi.
Mateu is a PhD student with the University of the Baleares in Spain, and he's based in Mallorca. He conducts his research in the group of Professor Jeroni Galmes, whose focus is on plant physiological processes of the adaptation of tomato landraces and wild tomato species to conditions of water shortage. And Mateu's work is linked to TOMRES work package 1, so he also looks at some of the resilient genotypes and identification of these. Mateu, the microphone is yours.
Okay, good morning, everyone. First, I would like to thank Hannah and the organizers for letting me talk in this workshop. So the title of my presentation is High-throughput phenotyping of the TOBC collection under combined stress in order to identify the most resilient genotypes. Nowadays, agriculture is facing two main problems. The first one is related with water scarcity. It is estimated that agriculture consumes nearly 70% of all extracted water in the world. It is predicted that climate change conditions will increase drought periods and evapotranspiration rates, increasing in turn crops' water demand. Also, it is expected that those drought periods will be harder in Southern Europe and in the Mediterranean countries. Another big problem that agriculture is facing is related with the use of fertilizers, which demand is increasing year by year. It has to be noted that fertilizers are limited resources, and also that European legislations are becoming more restrictive in order to protect water quality and biodiversity, since more of the applied amount of nitrogen and phosphorus fertilizers are lithiated in the soil. Therefore, there is a need to select the most resilient genotypes to combine it water and nutrient stress. In the case of tomato, land races have been generally excluded from breeding programs, despite most of them have been selected over centuries under salinity, heat, low nutrients, or drought environments. Also, most of them are recognized by their high fruit quality and shelf life. For instance, there is a group of land races labeled as Mediterranean long shelf life land races, which merge in three common and interesting traits, which are their increased drought tolerance, their large shelf life, which allows them to be stored after harvest up to 12 months, are their large and huge agronomic variability. So those three common traits highlight them as potential candidates to be included in breeding programs. Therefore, in order to explore the variability of some of those land races, and in the mark of Work Package 1, we explored the variability of 165 tomato genotypes under summer Mediterranean open field conditions. In order to better analyze our collection, we classified depending on two main traits, the fruit type and the cultivar type. Regarding fruit type, and since the collection, the genotypes of the collection were originally mainly from the Mediterranean basin, we found a big and large group of long shelf life genotypes. A second group of cherry genotypes, which didn't have the long shelf life phenotype, was also identified. All those genotypes with elongated fruits and which are usually destined to processing industry were labeled as processing. And finally, all those big fruits usually consumed in fresh or in salads and which didn't fit in any of the previous classifications were labeled as big size. Regarding the cultivar type, the collection was divided between land races and modern inbreeds. All these genotypes were cultivated under two treatments, control conditions and combined stress conditions. For control conditions, the full water and nutrient demands were covered all over the growth and the cultivation period, and for combined stress, fertirrigation was stopped 1 month after field transplantation. Here, I will show you some of the results obtained in our experiment. Here, for instance, you can see the leaf carbon isotope composition. On the left box for plants growth under control conditions, and on the right box for those plants grown under combined stress conditions. Leaf carbon isotope composition has been generally linked with plants' water use efficiency, having those plants with more negative values, lower water use efficiency, and on the contrary, those plants with more positive value and increased water use efficiency. Despite the large variability that we found in our collection, we can identify that long-shelf live land races were placed at the top right side of the boxes, indicating their increased water use efficiency as compared to other genotypes. A similar variability was found in other leaf-related traits, as the leaf nitrogen content or the leaf mass area. Regarding fruit yield, you observed a 20-fold variation in our collection under both conditions. Also, and despite the impact of combined stress was dependent on the genotype, we observed a general reduction of the 30% of crop production under combined stress. The large variability in yield was linked with the huge diversity of the genotypes in terms of fruit number and fruit weight. Finally, the impact of combined stress over fruit quality was more evident in the total soluble solids content than over acidity, despite all or almost all the genotypes significantly increased their acidity values under combined stress. Considering the large variability that we had in our field, we decided to analyze genotype by genotype the effect of combined stress. To do so, we built those two clusters, one for those plants cultivated under controlled conditions, and another one for plants growth under combined stress conditions. Those clusters were constructed using only agronomic parameters. And on the top of the graph, you can see the most productive genotypes, and at the bottom of the graphs, the less productive genotypes. We observed that those most productive genotypes under control conditions were also the most productive genotypes under combined conditions. And on the contrary, those genotypes with the worst agronomic performance under control conditions also had the worst performance under combined stress conditions. It is remarkable that among those highly resilient and productive genotypes, we can find some modern breeds which had as one of their parentals a long shelf life land race, confirming the large potential of those land races to be included in breeding programs. These graphs also allowed to identify those genotypes that largely decrease their agronomic performance under combined stress, but also to identify those genotypes that maintain or slightly increase their agronomic performance under combined stress, being also potential candidates to be included in breeding programs. When relating the different traits that we measured in this experiment, some nice correlations were found. For instance, when relating fruit production and leaf carbon isotope composition, and considering all the genotypes under both conditions, a negative trend was observed between both parameters. However, what is more remarkable of this correlation is that it seems that leaf carbon isotope compositions set a limit to fruit production, suggesting that this parameter, leaf carbon isotope composition, should be included in phenotyping platforms in order to easily assess the maximum agronomic performance of a genotype. In fact, most of the plant-based parameters used in this experiment are highly reliable. However, they are very time-consuming. On the contrary, the use of unmanned aerial vehicles allow us to obtain quick information and valuable information of our crops, and allows us to monitor the plant growth over the cultivation period, and depending on the equipped cameras, we can also obtain physiologic information of the plants. So, with the aim of relate plant-based parameters with remote sensing parameters, we used as a base the same experiment that I told you before, and we were able to measure up to 91 genotypes. In that case, we divided our collection depending on the genotype, if the genotypes were long shelf life or non-long shelf life genotypes. Here, you can see the results for two of the main remote sensing parameters that we obtained. One is the NDVI. NDVI is a multispectral index, and it's a proxy of the physiologic capacity of a plant. And CPA, which is the canopy plant area, and this is the proxy of how big was the plant. We observed that regardless of the cultivation conditions, long shelf life genotypes had higher values than non-long shelf life genotypes. When relating the NDVI, which is a multispectral index, with the most common photosynthetic traits, we observed significant relationship for all of them. In those graphs, the dotted lines refer to the relationships when considering all the genotypes and all the treatments, while the solid black lines refer to when only considering non-long shelf life genotypes, and the red ones to only long shelf life genotypes. However, an ANCOVA analysis revealed different progressions for non-long shelf life and long shelf life genotypes. And for the same NDVI value, long shelf life genotypes had lower net CO2 assimilation rates than non-long shelf life genotypes. Therefore, remote sensing accuracy was increased when screening the genotypes with similar physiologic behavior. The exploration of the use of remote sensing was not only limited to physiologic performance, but we also explored the relationship with agronomic performance. We observed significant correlations between fruit production and both NDVI and CPA indices. And the relationships were more significant when relating fruit production with canopy plant area. So fruit production was more related with plant growth than with plant physiologic status. Despite the scattering of these relationships was huge, we also aim to relate remote sensing and tomato fruit quality, and we observed significant relationships between the total soluble solids content and some multispectral indices as the NDVI or the simple ratio. As I said before, despite the scattering is huge, this experiment sets a first step to develop more consistent models which can help farmers to easily manage their crops under controlled or combined stress conditions. Considering the large variability and the differences among genotypes that we had in our field, now we aim to select the most resilient genotypes to combined stress based on fruit production. And while on fruit production, because fruit production is the last and the most interesting parameter for farmers. To do so, we performed a method following a two-step classification. First, we calculated the resilience factor for all the genotypes. The resilience factor is the production under combined stress as compared to the fruit production under control conditions. However, selecting based only onto the resilience factor would lead to wrong conclusions. So a second step is needed. And this step consisted in classifying our collection. To do so, we first classified the collection based in the 4 types or the 4 fruit types that I described before, which are processing, big, long shelf life, and cherry genotypes. However, the variability within each group was again too high, and we had to continue classifying our collection. To do so, and based on the fruit production under control conditions, we identified some production ranges within each fruit type. So finally, combining the production ranges within each fruit type and with the resilience factor, we're able to identify the 13 most resilient genotypes to combined stress. It has to be noted that this method didn't identify the most resilient genotypes or the most productive genotypes under control or combined stress conditions, but the most resilient genotypes based on the resilience factor within each production range and fruit type. In fact, when relating the fruit production under control conditions with the residence factor, we observe that the selected genotypes, which are those ones highlighted in red, are the ones that maximize their fruit production under control conditions with the maximum resilience factor. So in conclusion, we observe that combined stress led to a general decrease in fruit production and an increase in fruit quality. We also observed that some modern breeds showed a high resilience to combined stress. Also, that remote sensing accuracy was increased when screening genotypes with similar physiologic and agronomic performance. And finally, that the classification of the collection, depending on the fruit type and production, combined with the application of the resilience factor, allowed to identify the 13 potential genotypes to be included in breeding programs to enhance tomato combined stress resilience. And finally, I would like to thank to all the people involved in the data, in the experiment performance, data acquisition, and that helped me all over this process. And also thank you for hearing the presentation. Thank you.
Thank you very, very much, Mateu. And also thank you for building already a bridge with your presentation to our second workshop on the 15th. I should like to make a little an advertisement and invite those of the participants who have not yet registered to our second workshop on the 15th of March, that in that workshop we'll look further into the implications of TOMRES research to the praxis. And what you have presented, Mateu, is already linking up to what will be of particular benefit to the farming community of our research.